Okay, let's get started. All right, I'm effective today. No whistle needed. Okay, I just want to do go over a couple of recap questions with you before getting into the HPLC lecture. What is peak resolution? Don't look back in your notes, just whatever you remember. Jason. Separation of two peaks. Okay? So peak resolution is basically the resolution of one peak from the other. So separation of peaks. What is solvent front peak, Hayden?
The solvent front peak is that first peak that's going to be the HPLC is detecting your solvent.
Yeah, HPLC or GC. So it's the detector peak. So when the solvent hits the detector from the minute of injection, from the time of injection to the time of reaching the detector, that would be the solvent front. It's also known as the void volume. So the volume it takes of the volume of the column that is volume, that is void. That means the sample, if your sample does not interact with the column, it comes with the void volume. What's the difference between retention volume and retention time? Retention volume versus retention time. Why don't you know this? Sophie.
So retention time is how long it takes for your sample to move through the column, and then retention volume is the amount of solvent that you need to reach this part of the sample.
Exactly. So retention time is the time it takes for your sample from injection to detection. So how long it took for the sample to move through the column and get to the detector, and retention volume is the volume of the solvent that was used to get that sample to the detector at that particular time. So we usually don't worry about retention volume, we usually use retention time for detection needs. What's the relationship of peak width to resolution? That means if you have a wider peak, what does that mean, versus a narrower peak, what does that mean? Anna?
I think the wider peak is worse resolution, while a sharp peak is better resolution.
Exactly. So the sharper the peak, that means you reach equilibrium faster. So that means you have a shorter height equivalent of a theoretical plate. That means you reached equilibrium in a shorter amount of time, and the peak, your sample did not diffuse within the column. It continued moving in and out between the stationary phase and the mobile phase. So it maintained a sharp peak throughout the column, or sharp band throughout the column. So the narrower the width of the peak, that means you have better resolution. Okay, what is the first step in developing a separation between solutes of interest in your sample? First thing you do, Hayden?
Read about it.
Read about it, yes. So you read about it, see what other people have done, what did they do to separate their components, what stationary phase they used, what mode of separation they've used, and then go from there as a starting point. How does temperature impact resolution? With higher temperature, what happens? Tia? Say that again. Lower viscosity and better resolution. So you have lower viscosity of the mobile phase. That means the movement is faster through the system. And also the movement of your solute is faster due to thermodynamics. So everything is moving faster. Equilibration is reached faster. That means you have sharper peak, better resolution, shorter analysis time. But again, you have to always find the sweet spot. So you don't want to have really high temperature. First of all, your column has a range of temperature that it withstands. So you don't want to go to high temperature so that you don't damage your stationary phase. Also, you don't want too high of a movement. That kind of has an opposite effect. So you might not reach equilibrium because it's moving too fast, or samples won't have enough time to separate. They will be moving together, so you will have co-elution. So you don't want really high temperature, but a little bit of a temperature or higher temperature helps with resolution and time, analysis time. What about flow rate? Brigitte?
If the flow rate is faster than, is higher than the solvent will move faster as well, and you will decrease the time needed. But also, if the flow rate is too fast, it will use leach faster, and like the separation will not be as fast.
Exactly. So if you remember that equation of the efficiency with A plus B over mu, which is flow rate, plus C U. So the U is the rate of the flow rate, that is. So it has two different effects. So if too high of a flow rate is not good and too low of a flow rate is not good. So you want to choose a flow rate that will give you the lowest height equivalent of a theoretical plane. So a higher flow rate helps with reaching equilibrium faster, maintain that sharp peak. That means you have better resolution, but also too fast of a flow rate, things will move too fast. You won't have enough time to separate, to reach proper equilibrium, then you will have co-elution of your peaks. So you do not want to have too high of a flow rate or too low of a flow rate. How does the packing and thickness of the stationary phase impact resolution? I don't know if I talked about it a lot last time, but I just want to demonstrate a little bit. Sometimes you have a packed column, and we'll talk about it a little bit more later. So you have your, in Hplc at least, you have packed column where your stationary phase is packed within your column. Or you have a hollow column where your stationary phase is really on the sides of the column, like a thin layer on the column. So you only have a little bit of room for your sample to go in, not a lot. So not a lot of a diffusion, so not a lot of surface. Whereas here, your stationary phase all over is packed in the column. So you have pores, and you have your packing material, and then you have the pores within each packing material. So there is a high chance of going in and getting diffused in your stationary phase. Whereas here, when you have a thin layer coating the inside of your column, you don't have much of a space for your sample. So you reach equilibrium faster, basically. So reaching equilibrium faster, that means you get better resolution or sharper peaks and shorter analysis time as well. So that answers that question. But the only difference here is the loading, how much you load on the column. So if your sample is too concentrated, it will not work well with a thin layer of a stationary phase. So you just have to adjust how much sample you load on the column when you're using a very thin stationary phase. So advantages of a narrow diameter, I'm not sure I talked about that either, but when you have a longer column and a narrow diameter, again, this enhances resolution. Okay? You don't have a lot of stationary phase, and you have a long column where the sample has time to separate based on its affinity to the stationary phase, so you have better resolution. Okay? And also you have sharper peaks. That means you have higher height versus if you have a smaller peak but yet a little wider, your absorption here is not a lot compared to absorption here. So here you basically have better sensitivity. So when you have sharper peaks, longer height, that means you have higher absorption. So this way you get better sensitivity of your detection. So when you have narrower diameters or thin stationary phase, you tend to have better sensitivity because your peaks will be higher, an indication of a higher absorption at the narrow range, rather than spreading over, so that if they spread over, that at any time point, you have smaller concentration coming out. With smaller concentration, you have less absorption. But when the peak or the band is narrow, you have really here the highest concentration, then you have a higher absorption. So these little concentrations are really more concentrated in one tiny narrow band. So you can see higher absorption, you enhance sensitivity that way. Okay, the rest are related to HPLC, which we haven't started yet. So originally, HPLC stood for high pressure liquid chromatography. So it stood for high pressure because you have these columns that are packed under high pressure, and they are packed in such a way to minimize void as much as possible. With that, they generate really high back pressure when you put them in the system. But with time, the equipment and the columns are packed more efficiently in a way they do not produce as much of a high pressure, but they become, the P transform to high performance liquid chromatography. Still higher pressure than low pressure liquid chromatography, but it's not as much back pressure as it used to be due to most advancement in column production and also in the analytical system itself. These are actually made up of your samples that you ran with HPLC. A few years ago, I had a creative TA that made this out of Pepsi and coffee and tea and all of the samples. So compared to traditional low-pressure liquid chromatography, with high-performance liquid chromatography, analysis time is faster, so we enhance the speed. You enhance the resolution because your particles are packed in a manner to avoid as much void as possible. And when you have lower void, you have less spaces for your solute to diffuse into. So it will just move down as a narrow band. So you enhance resolution. And the columns are reusable and you don't pack them yourself. You purchase them already packed, and they can be used for as many as 1,000 injection, and if you take care of the column and regenerate it and clean it every time, it can last longer. So they're reusable columns, but they're very expensive columns. So the column can range from $800 to $2,000 depending on the size and the material. So they are expensive but reusable. And then easy sample recovery, that means you can collect samples and the samples are purer than they would be with low pressure liquid chromatography. I want to show you now a video with the English accent video.
Food products and industrial chemicals. The purpose of this guide is to consider this question: what is a HPLC instrument? We will focus on analytical applications. The implementation of HPLC requires the use of precision instruments. There are two main reasons for this. The first is that sophisticated instrumentation is needed to create understanding of the components common to all HPLCs can transform bewilderment regarding a complicated arrangement of tubing and electronics into an appreciation of a logical and well-designed piece of analytical equipment. At the heart of all HPLC systems is the column. This is where the separation of the components of interest in your sample actually takes place. It is the interaction of the stationary phase contained in the column, the mobile phase, and the sample components, which forms the basis of this analytical technique. The stationary phase in your column is typically, but not always, in the form of very small spherical particles. The diameter of these particles is in the order of a few microns. That's 1/1000th of a millimeter. In analytical HPLC, the particle size diameter ranges from approximately 1.5 to 10 microns. To achieve a separation, we need to create a flow of mobile phase through the column. To enable this, tubing is connected to the ends of the column. The very small size of the particles means that a flow of liquid needs to be pushed through under high pressure to get a reasonable flow rate. As a consequence, the tubing needs to be connected in such a way so as to withstand the high pressure. This is achieved by the use of compression fittings. These fittings screw securely into the ends of the column to create a leak-free connection. So far, we have a HPLC column connected by tubing and compression fittings to the mobile phase reservoir. We will add a vessel to collect the waste at the other end of the column. To keep the mobile phase moving through the column at a steady flow rate under pressure, we need to introduce a pump in the flow path. This instrument is designed to draw the mobile phase from its reservoir and deliver it to the column at the required flow rate. Now we have a flow of mobile phase through our stationary phase, but we need a way to introduce the sample for analysis. For this, an injector is required. This instrument is designed to inject a small aliquot of sample, typically in the order of a few microliters, into the flow path of the mobile phase prior to the column. It has to do this without altering or stopping the flow of the mobile phase, and thus maintaining the system pressure. In most modern systems, this process is automated, and samples are placed in vials which can be injected by the autosampler in the order and amounts programmed by the operator. When the sample has been injected and passes through the column, the separated components need to be detected in some way so as to convert the results of the analysis into useful data. The detector is designed to be able to recognize some characteristic of the sample component. The most common detector is probably an ultraviolet or UV detector. This works by passing a beam of UV light through the flow path of the mobile phase, measuring the absorbance. For those components which absorb UV light, the response obtained will be proportional to the amount of the component present. Not all components absorb UV light, and those that do have different responses, so these factors need to be considered when choosing a suitable detector. There are a range of different detectors available, which may be used for HPLC. These include MS, which passes the flow coming out of the column into a mass spectrometer, thus obtaining information on the amount and molecular weight of the compound. Other detectors which you may have encountered include evaporative light scattering, charged aerosol, fluorescence, and conductivity detection. Some kind of processor is required to convert the responses from the detector into usable data. Purpose-designed software applications called chromatography data systems are available. Common examples are mPower, Clarity, Chromalion, and EasyChrome. In gradient analysis, the composition of the mobile phase is changed during the course of the analysis. To enable this, we need another mobile phase reservoir and some way of mixing the two. The mixing may be performed before the pump, as shown here, in which case it is not yet under pressure and is called low pressure mixing. Or the mixing may be performed after the mobile phase flows through the pump, in which case it is under pressure and two pumps will be required. Systems which use high pressure mixing are often referred to as binary systems, since two pumps are needed. In practice, low pressure mixing with a proportioning valve before a single pump is most commonly used. Another instrument which is typically included in a HPLC system is a vacuum degasser, since all air needs to be removed from the mobile phase for optimum performance. Temperature is an important method parameter which needs to be controlled in HPLC. analysis. For this reason, the column is often housed in a compartment which can be temperature controlled. Many Hplc systems have the capability to mix 4 mobile phases. These are known as quaternary systems. So what happens during an analysis? The mobile phase is flowing through the system from the mobile phase reservoir to waste. We will inject a mixture of 3 components, shown here using 3 colours: pink, green and blue. At the head of the column, when the sample first encounters the stationary phase, we have a mixture of all 3 components. The equilibrium between each component, the stationary phase and the mobile phase is different for the 3 colours in the mixture. In our mixture, the pink component spends more time in the mobile phase relative to the green and the blue and travels through the column quickest. The blue component, however, spends more time on the stationary phase relative to the other 2 and travels through the column slowest. As the mixture passes through the column, they become more and more separated. The pink components leave the column first, and on passing through the detector, a peak is observed on the processor. Then the green component passes through the detector, resulting in another peak, and finally the blue component passes through and has a corresponding peak. This plot of the separated peaks is referred to as a chromatogram. Overall, the blue component spends more time in the flow path and has more time to spread out. This results in a broader peak relative to a component which is passed through in a quicker time, such as the pink in this example. It depends on the actual method parameters being used, whether this band broadening effect is as noticeable as it is in this example, where you can see that the peaks are progressively broader as time passes. Now that we have looked at the individual components of a typical Hplc instrument, you should be able to look at the system that you use in your laboratory and understand how it works. This video is provided as an example of the training resources available for more training services. Visit the website for more information on our training solutions for pharmaceutical analysis. Please feel free to use this video in your Hplc training programs.
Okay, I hope that was beneficial, not put you to sleep, and you may. Okay, so here are your components one more time. So if you have only one solvent and one pump, usually you're running isocratic elution. That means you're not changing the concentration over time. But often we do run gradient elution. So you have systems like you've seen, most of you seen in the lab already, except for 2 groups. We do have 2 pumps and 2 reservoirs. Some systems have 3, some systems have 4. So it can be binary, tertiary, or quaternary systems. So the mobile phase in the reservoir is being pumped into your system. So there is a pump, and then goes into the injector where you inject your sample, and then the mobile phase carries the sample with it onto the column. And from there you have interactions, and then the samples get separated, and then each component reaches the detector, hopefully separately, and gets detected. Then from there you can either goes to the waste, or you can have a fraction collector where you can collect each component that you wanted to purify for further analysis. So you can use fraction collector there. So the pumps are automated in Hplc, and they have constant pressure and pump constant volume in a certain period of time. So the flow rate, so you can control the flow rate of the pump, and however you change the flow rate, the pressure is impacted. Okay, so if your pressure, if you increase the flow rate, usually your pressure goes up. And also if you add different components to the system, let's say you have a column and you add a guard column, the guard column is going to add back pressure to the system as well. But usually you have a certain maximum that the pump can withstand, certain maximum pressure. And if all of a sudden your pressure just peaked, you would say, okay, there's either something blocking my tubing, so you check that your tubings are not blocked, or maybe the guard column is at full capacity, and I'll talk about guard columns in a second. that means they are full of impurities and causing a back pressure. And then that's when you change the guard column. Sometimes you change the guard column, but it's also high pressure. That means your column has been blocked as well, and that requires a change of the column. So changes in back pressure indicate something's off with your system, and it kind of guide you towards what you need to do. You need to change tubings, you need to change filters, you need to change check valves where your mobile phase are coming in. So something is being blocked that you need to fix. And then when you have, let's say you have one pump and then two mobile phases, there is something we call low pressure mixing. So that you have a mixer before they enter the pump. So you have the two solvents, and then before entering the pump, there would be a mixer that would mix them, and then they would enter the pump, and from there get pumped into the injector. So that is what we call low pressure mixing. High pressure mixing is more desired because then you have two pumps. Each pump is pulling out the mobile phase under pressure, and they're mixing it under pressure. So the mixing is more efficient. And then you get more homogeneous mobile phase and less risk of having spikes in your baseline. So you would have a smoother baseline because your mobile phase is mixed properly. So after the mobile phase gets pumped in, the first place it would go is through your injector. So where you inject your sample. So you can have an auto injector, and most of you seen that in the lab, where you have a tray, you put your samples in that tray, and then you have a needle that automatically moves to a location based on the program. And then it gets, it goes through the septal of your of the cover of the cap and pulls out a certain amount of volume that you program it to do that, and then gets it into a sample loop. So there are different sizes of your sample loop. You can actually get as small as 20 microliter sample loop and as big as 200 microliter sample loop. And in between, you can actually get them and you can cut them yourself into the sizes that you want. And you attach them to the injection port, and the sample gets injected into that injection port, and from there valves are open to allow for the mobile phase to pass through, pick the sample, and continue its route to the column. Now, there are manual injectors. We also seen that in the lab. Manual injectors, that means you fill your own syringe, and then you inject your sample at the load position, and then you turn it to inject to open the valves manually and allow the mobile phase to go in and pick up your sample. Stability can be a factor. So if you're running 50 samples and some of your components that you're analyzing can be degradable over time, like for example, some can get oxidized or temperature sensitive or light sensitive. So what you would do, usually you have your samples in a compartment that is closed so they're not exposed to light. And another compartment that can be added is a cooler. So your tray here can be cooled down to refrigerated temperature so that during the run, you have all of your sample at cold temperature so that you avoid degradation over time. Having auto sampler obviously is time efficient and reduces errors from the human error from injecting the sample each time, or introducing air bubbles when you inject the sample if you're not very careful. So it's more efficient to have your auto injector, but sometimes you end up having a manual injector just because of cost reasons. So it's cheaper to have a manual injector over an auto injector. Then you have your columns. So after the injector, when your sample is now moving through, it gets to your column. So we have so many different types and sizes of columns. And usually they are in a stainless steel, made of a stainless steel, and then your stationary phase is placed inside of that. And they get different length and different thickness. Of course, depends on what you're trying to inject or what are you trying to separate. So different sizes and dimensions. And the pre-column, or we call them guard columns or guard cartridges, they are basically components that you put them prior to before the column. That means when your mobile phase is moving, the first it will hit the guard column and then the column. From its name, it's guarding something. So basically, it's guarding the column from impurities that could be in your samples. And it's made up of same stationary phase that is in your column. So the same material. If you have a C18 column, you have a C18 cartridge or C18 guard column. That means you have the same material ahead of your column. It's capturing, if it is a reverse phase C18, that means it's capturing all components in your sample that are very hydrophobic and might bind irreversibly to your column. That means they might bind and block some functional groups, and if the functional groups are blocked, that means they are not available for your samples to interact with, so you lose efficiency. So the guard column is basically capturing everything, all the impurities before it gets onto the column. So it captures the impurities and the rest of the samples continue. Those that bind strongly to the material will remain with the guard column, and those that bind loosely will continue their path to the column and get separated and move on. Eventually your guard column will get saturated. That means they reached capacity. So all of the functional groups on your guard column is being blocked by impurities. If you leave it there, that's when your back pressure will go up, and you'll know that, okay, I need to check my guard column, I might need to replace it. And usually every column comes with 3 guard columns. You would purchase 3 guard columns per column, so you replace it at least 3 times during the lifetime of the column. So there are different types of Hplc columns. So you have the microbore and micro columns. So you have the microbore that have internal diameter of 0.5 to 2.5 millimeter, and then the micro columns are smaller with less than 0.5 millimeter in diameter. So there is the packed microbore and micro column. That means your stationary phase are packed throughout. So there is no hollow tube in there. Or you have the capillary, where you actually, it is a hollow tube with your stationary phase packed on the walls. So ultra Hplc, usually you hear the term ultra Hplc, they mostly function with the small micro columns they operate, and mostly these will be capillary columns. So it's high performance liquid chromatography, but it's called ultra because it works with very small columns and very narrow diameter, and mostly they're capillary columns. So they're high efficiency. You get maximum resolution that is possible with high performance liquid chromatography, but you work with a very dilute samples. You cannot load a lot of sample. So they're not used for purification or anything, mostly for detection and identification. And oftentimes, ultra Hplc is linked to mass spectrometry. So you would use very small amount of samples, you get maximum resolution that is possible, and then enhanced detection with mass spectrometry. So, talked about this earlier at the beginning of the lecture. Yeah? All of the above, Michelle, that's correct. So with narrower diameter, you have less packing material in there. And what happens when you have less packing material, you have enhanced resolution because you reach equilibrium really fast, and then you would keep the band sharp as it goes down. And with keeping the band sharp, you have high height, and with having high height, you have better sensitivity than a broad peak. So all of the above. So the packing material of the column, so it has to be sturdy. That means it needs to be used as support as well. So and withstand high pressure. And it should have well-defined particle size, so small and well-defined particle size, good mechanical strength, chemical stability over a range of pH. And then the pore size or pore diameter, it varies depending on the particle size, but the smaller the pore diameter, the better for resolution. So the different packing materials, so it can be bonded phase. So for example, you have silica and then you have the bonded phase here. The bonded phase represents the R group here. The R group could be a hydrophobic group, like in reverse phase, could be hydrophilic in normal phase, or could be ionic, so it can be used for ion exchange. So in this case, the bonded phase can be any type that facilitate different modes of separation. Molecular packing material is when you have an inert core, that it means it does not interact with the sample, it's not porous, and on the surface of the inner core, you have thin layer or coating. And that means you have very small amount of stationary phase. Again, with this much amount of stationary phase, you cannot load a lot of sample, but you get a lot of enhanced resolution. Since you don't have, the sample does not stay on the stationary phase as long, it reaches equilibrium faster. Again, the functional groups in the thin coating can be ion exchange, or it can be normal phase or reverse phase or anything. The rigid core will withstand, would have good physical strength and withstand high pressure. And like I said, the thin stationary phase provides better rapid separation and better resolution. Two other types are the porous type. So we have the micropores and then a mixture of micropores and macropores. So in this case, you would have, you would separate based on the size of the molecules. So you can have large size gaps or very small gaps. This means if you have large molecules, you would use micropores. Only if you have small molecules that you're trying to separate, then you would use a highly cross-linked matrix. Column Alvin, we talked about the temperature, so you would want to regulate the temperature because the temperature in the room fluctuates. So sometimes it's cold in the room, sometimes it's hot in the room. So when it's cold, you'll notice that your retention time gets delayed, because now your mobile phase is thicker, viscosity is higher, solutes are moving slower, so you will see a delay in your retention time. And when the room is hot, you see that everything is moving faster, you have better resolution, quicker analysis time. But in order to have consistency in your analysis, you tend to have these ovens where you put your column in the oven and then maintain a particular temperature that would work best for your analysis. Again, how do you determine the optimum temperature? Is basically by experimentation. So you would just try out different temperatures and see which ones gives you the better resolution and shorter analysis time. Detectors. So let's spend a little bit of time talking about detectors. HPLC detectors. So the most common HPLC detector are the absorption detectors, where you measure either UV absorption or visible light absorption. So with UV vis detectors, you are measuring the ability to absorb light. That means you have to have a chromophore. That means a compound that can absorb light. So proteins can absorb light, polyphenols can absorb light. So here is one of the most common UV detector. We call it variable wavelength detector. So those of you that did the HPLC lab, we have one of the two detectors we worked with is the variable wavelength detector. That detector would have two sources of light. One is a deuterium and the other is tungsten lamp. So the deuterium is for UV absorption or for UV light spectra, and tungsten is for the visible light spectra. So with variable, it's called variable because you can actually choose a wavelength to measure at. So it allows the selection of a particular wavelength of choice that you would select based on your knowledge of which wavelength will give you maximum absorption. So lambda max, that means the wavelength at which you get maximum absorption. So if you know that about your product or your compound, you can select that wavelength and get measurements or absorption at that wavelength. So it functions by using a monochromator, and then we'll talk about the monochromator when we start talking about the spectroscopy coming up next, either Wednesday or Friday. So that means this component here select one wavelength from the light. So the light comes out and it gets diffracted into multiple wavelengths, and the monochromators select one wavelength for their sample to absorb at. So that means we need to know which wavelength to select that gives us the highest sensitivity. You can, some units, you can actually set a change in wavelength during a run. So if I know that in my components, I have one component that absorbs the max at 249 and another component absorbs the max at 259, which is very typical in isoflavones analysis. For example, you'll do that next week. Those of you that are doing a mass analysis will be looking at those different components next week. So if I know that one absorbs at 249 max and the other at 259, that during the run I can adjust my variable wavelength detector to, from time 0 to time 15, select absorb at 249, and then from time 15 to time 30, absorb at 259. So I can actually set my program to allow for that. Another common detector and more powerful detector than the variable wavelength detector is the photodiode array detector, and we use that in lab to do the scanning for the caffeine in the HPLC lab. So here in the photodiode array detector, the light, all of the light from a deuterium lamp or a tungsten lamp gets spread onto your sample as it goes through the detector and in the flow cell, and then the light, after the sample absorbs light at different wavelengths, the light goes onto an array of photodiodes, with each one of those photodiodes convert the photon of light to electric signal, and you get a spectra. That means you get absorption. So you have absorption here. And I think it's at 0.1 second. Every 0.1 second, you get an absorption spectra over a range of wavelengths. If we're looking at UV, it can go up 200 to 400 or 450 nanometer. And then you get a spectra. For the caffeine, we got a lambda max here of 272 nanometer. That means for the caffeine, we had maximum absorption at 272, and it absorbed at 250, I believe, up to 300. At 315, it did not absorb light. So that was the spectra that most of you seen in the lab. So this was a unique for caffeine. So every compound that absorbs light, every chromophore that absorbs light, will have its unique spectra, because every chromophore absorbs light differently. So this kind of spectra helps me identify my components. So I don't only rely on retention time, I look at the spectra and I have a better idea of what the component is. So something we saw also in the lab with most groups so far is that the PDA tells me if my peak is pure or not, if there is a coelution. If there is a coelution and I'm just doing the variable wavelength detector, I will only see one peak at that particular wavelength. I won't be able to know if that peak is pure or not pure. However, with the PDA, I can see spectra. I can see that this is the absorption spectra of one compound and this is the absorption spectra of another compound. So I can tell that this peak is not pure because now I have two different spectra that I'm seeing. So that is the power of a PDA. It really is more for detection and identification than just measuring absorption at a particular wavelength. Fluorescence. So some compounds fluoresce. That means after they absorb light, they emit light. And usually emission of light is more sensitive, so you can detect lower concentration than by regular absorption. So it's often used for vitamins detection and aflatoxin, and also it can be used in amino acid composition analysis. So in fluorescence spectroscopy, you would set to absorb at a particular wavelength. So you set the absorption wavelength and also you set the fluorescence wavelength. And also you set those that will give you the highest sensitivity. So you would monitor at two different wavelengths, one for absorption and one for fluorescence. And we'll talk more about that in the spectroscopy lectures. Refractive index is another common detector, often used with carbohydrates analysis, very commonly used there. It basically measures the refractive index of the mobile phase, and when you see when the mobile phase is carrying a sugar with it, then the refractive index changes, and it monitors that change. With the refractive index detector, we cannot use gradient elution. Why is that? What happens with gradient elution? Too many changes. Your mobile phase is changing. It's not like it's not detecting the compounds based on their characteristics. It's just detecting a change in refractive index. So it's not very specific to a carbohydrate or a lipid or change in the mobile phase. It just changes the refractive index. So it's not very specific. So it's really, you cannot use gradient elution. You have to use isocratic elution with refractive index detection. Electrochemical detector. So it has two phases. The electrochemical detector, it can detect based on oxidation reduction of the analyte. So it measures a change in current, or what that would be with pulse amperometric detector, MPA in this, not MPA, PAD. And then also you can measure change in conductivity if you have ions. So if you have ions that you're separating or separating compounds that have ionic charges, then you can measure a change in conductivity. So either change in current due to oxidation or reduction, for example, for phenolic compounds, Or you can measure change in conductivity for ions. So you can use that for organic acids, or you can also use that for amino acid composition because they carry charge. Light scattering, it's a universal detector, so it can detect anything, but you have to evaporate the solvent. So what happens that your compound is traveling with the solvent, and then it reaches the detector, and then you evaporate the solvent, and what's left is the particulates, the compounds, and they will scatter the light. And then you measure the extent of light scattering. Okay? A very common detector that is used with size exclusion chromatography is MALS, which is the multi-angle laser scattering detector. It's a very sensitive detector and allows for accurate determination of molecular weight. Another detector is mass spectrometry, and Gary's going to talk about that next week with you. So it's basically, and you're going to have a lab about it. So it detects and provides you molecular information. So it gives you first the molecular weight. You can use it to determine molecular weight, and you can have fragments. You can get the molecular weights of the fragments and kind of piece them together and do identification of the original compound. Chemical reaction, basically, if you have a compound that does not absorb light, you can react it with another reagent. So OPA, for example, is a reagent, or ninhydrin is another reagent. But with OPA, if you react, let's say, your amino acid with OPA, it gives you a compound that you can absorb light, a chromophore. Same with ninhydrin. And then once you have a compound that absorbs light or fluoresces light, then you can measure absorption or fluorescence. I went over. Nobody said anything. You're sitting quietly and politely. Thank you.